Okay, everyone, so it's time to begin. And I just want to tell you that the calendar's been revised. We're not going to cover quite as much material before Exam 1. I changed it from going all the way up through Chapter 20 to now just up to Chapter 18. And in fact, we're going to skip Chapters 19 and 20 because I want to take it a little bit slower. I felt like we were going too fast, and so I'm going to take it a little bit slower. And Chapters 19 and 20 are great. They're about power calculations, but they're not, we don't use them later on. So I want to spend more time on regression instead. So that's the new schedule, and in keeping with that, what I did was, okay, so now what's up now and posted are these pre-lectures through Chapter 13. So we're going to cover 12 and 13 today, and this is the beginning of significance tests. So, I mean, if you have a chance to do the pre-lectures before the lectures, that's great. That's better, but if you don't, you can do them afterwards. That's why they're not due till the end of the week. All right, so we're going to cover Chapters 12 and 13, and then your homework here is posted, and it covers the end of Chapter 11 and 12. And then your next homework will be 13 and 14. And that's what we're going to cover here. Okay? So that's the schedule. And any questions on that? All right. So now we left off, let's go to the document camera here. And we left off here on page 67. So we were talking about confidence intervals. And a confidence interval, remember what we do, we make a point estimate. Like if we have the sample average and we want to estimate the whole population average, we take our point estimate, which is the sample average, and we attach a margin of error to that. So a margin of error, we said, was plus or minus some z-score. This is how, okay, so we already said from last time that a margin of error, that's the little bit of wiggle room we attach, the interval we attach around our point estimate. And it can be we can be a 95% confidence interval in which you'd have two standard errors, but in general, it's a margin of error is some z statistic or t statistic. We'll just talk about z now. Some critical value of z times the standard error. So if you're 95%, you want a 95% margin of error, you would have 2 for your, it's the z star corresponding to this middle area right here. That's how confident you are. So z star is like right here. And this, for like 95%, you'd have a -2 and a 2. Okay? So that's what we're doing here. So now the question is, how many people do you have to poll to achieve a certain margin of error with a certain amount of confidence? So let's look at this. So in a pre-election poll, this is very important. If you're planning a poll, you want to know, you want to have a certain margin of error and a certain level of confidence. Let's say you wanted a 95% confidence interval, and you wanted a margin of error of 3. That's very standard. Well, how many people would you poll? Okay, so first of all, it's a close race here. If it's a close race, what does that mean? The standard deviation, because we're going to use this for our margin of error right here. The standard error is going to be SD over the square root of n. So we need to know what the SD is. So if it's not given to you, but here it says it's a close race, you can assume here that the SD is equal to 0.5. All right? So we're given that the margin of error, this is what we want, is 3%. All right? So 3% margin of error. So our margin of error, remember, it's that what we attach to our point estimate. So that's our z star, our critical value. Here it's going to be the critical value associated with 95%. Okay, that's what that's going to be. A margin of error times some standard error. And we're talking about percent, so it's going to be the standard error for percent. So we say that's 3%. Okay? So now we can substitute in here 2, or 1.96 if you want to be really exact, but most people aren't. This is just an estimate of about how many people we need to pull. So you should be able to do this in your head once you see the formula. So this is 2, right, corresponding to the 95%. That's where that comes from. And then the standard, what is our standard error percent? Well, that's, you should know it's standard error is a standard deviation, and now you multiply or divide by square root of n. Well, for sampling, you always divide by the square root of n. The bigger your sample, the smaller your error. So you always divide for sampling for averages and percents. The only time you multiply by square root of n is when? For sums, for like gambling games or something like that. Otherwise, you're dividing. All right? And now, because you have this percent here, we're expressing it as 3 instead of 0, instead of a decimal, instead of 0.03. We're expressing it as a percent here. We're going to multiply by 100. So that's where this 100 comes in for that percent. Okay? So that's the same, that's this formula right here. Z times SD over square root of n times 100. That's what we're using. Okay. And now all we have to do is plug in what we have for SD. We say it's 0.5, and then solve for the square root of n. All right, so we'll go. So we have 2 times 0.5, that's from right there, times 100 over the square root of n equals 3. Okay? Well, now with a 95% confidence interval in a close race, 2 times 0.5 is 1. So this is just 100 over square root of n. That will come up a lot. So now you have 100 over square root of n. Often if you're doing, you assume that the standard deviation is about 0.5 because you want to make a conservative estimate. You're not sure what it is, and that's the biggest the standard deviation of a 0-1 box can be. So this, and 2 is a 95% confidence interval. So this 100 over the square root of n is basically what so many of the margin of errors in real life boil down to, what the calculation you'll be doing. Okay, so now we want to solve for n. So multiply both sides by square root of n, and, right? And then divide both sides by 100, and what do we get? We get divide by 3. We get square root of, we get n is equal to 100 over 3 squared. Okay? All right, now, if our margin of error, what do we get here? That's what? It's about 30 squared. So that is, if we did it exactly, n is equal to 1,111.111. Or we'd probably round up because we're counting people. So you'd round up in this case to that. That's how many people we'd need. And that's why so often you see these polls of about 1,000, because they're trying to achieve a margin of error of 3%. So any questions on that? The general formula would be what? What would the general formula be? So you could start from scratch here, but the general formula, you can see right here, in general, for percent, and you wanted to solve for n, if you wanted to use a formula, it's nice to look at the formula because it shows you as n gets bigger, your margin of error gets smaller. Or as your margin of error gets smaller, n gets bigger. Okay, so it's just z star times your standard deviation times 100 over the margin of error squared. Okay, so it's very easy to do it out or to just use that. All right, so a 90% confidence interval. How would we do that? What if it was a 90% confidence interval? Well, a 90% confidence interval would only have 90% in the middle, so z star would get smaller, right? So if you only want to be 90% sure, you're not going to have to sample as many people. So what would you do? If you use that, you could put what? You could say for 90%, it's 1.65. Between 1.65 and negative 1.65, I happen to know that it's 90%. You could look it up on our table. So you just say 1.65 times 0.5 times 100, right? That over the square root of n is equal to 3. And you could do the same thing, or you could just plug it in there. And you'll get n equals 756, okay? 0.25. So we'll round up to 757. So, let's say you had a margin of error, another example, let's say you only wanted a margin of error of 5%. What would you do? It would be, if you kept it for a 95% confidence interval in a close race, you'd just put a 5 in here, and you'd just get only 400 people. If you wanted a margin of error at 10%, you'd only need 100 people, etc. Okay? So, in calculating how many people to poll, we assumed the SD of the box to be 0.5, which is the biggest, so it's the most conservative estimate, and that's what people usually do. But if we knew that the SD was really less, say 0.4, how many people would you need to poll here? So if it was only 0.4 using that formula, what would we get? We'd get 9 equals, if we kept it at 95%, it would be 2 times, instead of 0.4 times 100 over 3 squared. So if there's less variability, if your standard deviation is smaller, less variability, well, then you don't need as many people, right? So this would be if there was like a 80%, 20% split, you'd get 0.4, right? Instead of a 50-50, it would be an 80-20. If you knew it was going to be a lopsided split like that, you don't have as much uncertainty. So then you'd get a smaller one, because it's 0.4 instead of 0.5 here, right? So instead of n equal this, you're going to get something smaller. Okay? Any questions on that? Now, sometimes we might want to use this one right here, the margin of error for means instead of percents. The only difference is you don't multiply by 100. And when would that happen? That might happen, for example, at our grading meetings, when we want to decide whether we want to scale the grades, we want an estimate, or how hard or easy we want to grade things. We might take a random sample out of the thousands. Like for Stat 100, we have to grade like almost 2,000 exams. So we might take a random sample first to see what the average would be. Okay, so how big a random sample would we need to take if we wanted to get a really small margin of error of 2 points for the average with 95% confidence interval? Now, the standard deviation of the class is usually about 10 points. So now what would we do? So we could use this formula again, n equals z star times the SD. And now we don't multiply by 100. Why? Because it's an average, right? We're using this formula here over the margin of error squared. Okay, so now this is a z star. Okay, so then what would we get? We'd get n is equal to 2 for the 95% times our standard deviation is what? 10, so that would go in here. And if we assume this margin of error at 2 points, that's our margin of error here. And so that would be 100. That would be a lot. If you just, I mean, you don't have to remember this formula. You could easily do it. You could say, okay, what is a margin of error? Our margin of error is a z, our critical value. It's how many standard errors, right? How many standard errors times our standard error. In this case, we're talking about averages. So we'd say, okay, we want what? A margin of error at 2. And we'd say, okay, if we want a 95% confidence interval, we want 2. And then this is SD over the square root of n. Okay? So we just say 2 equals 2 times our SD is 10 over the square root of n. Right? So then we'd get the square root of n is 10. So n must be 100. We get the same thing. there's no, this standard of error, this has a lot. What if I wanted to increase it by, that's a lot to grade. So I'd say, what if we were willing to take a standard error of 4, like repeat A? Let's just, instead of doing this one, let's do C instead, because it would come up more. So why don't we say repeat, and you can do this one on your own if you want. Repeat A with a margin of error of what, let's say? Okay, I'm willing to accept a margin of error equal to 4 points, because I don't want to go, I want to reduce that. Can you see now what's going to happen? Instead of dividing by 2, if I double that and divide by 4, do you see what will happen? Then what will happen? I'll get what? 2 times 10, and I'll have a 4 here. So now, then what's this work out to? This is only 25 then. So doubling my margin of error made me, because of the square root law, that square in there, reduce my n to 25. I only get 5 squared instead of 10 squared. It's because of this square here, the square root law. Okay, so you can do this one on your own. Well, if you want to do this one, it's so easy, we could just do it right now. So B, what would that be? If we put 12 in there, we'd have what? N equals, it's the same thing we had before, just put a 12 in there. So you'd say 2 times 12 over 2 squared. So that's just 12 squared, which is 144. So for standard error, 12 is about the biggest it's ever been. So that's part B. All right, any questions on any of that? So now significance tests. All right, so significance tests are super important. And of course, this summary is important, so always read it. Always read these summaries. And here's a chart. If you're not sure whether to use Z or T, this might help you. Now, significance tests are hypothesis tests. They're the same thing. And they come up all the time when we want to make decisions. We want to decide, for example, whether a treatment worked or not. So maybe we should go back to like the very beginning of the class, page 4, because we said there on page 4 that we're going to, that one of the reasons right here that random controls are really important is because they allow us to do these significance tests. So let's read this again. Remember what we were doing here. We were looking at, okay, why randomization is important. It's because it eliminates bias. But then we also said that if we translate things into a box model, a chance process, like we've been doing, if we then we can see, when we see some difference between the treatment and control groups, we'll be able to, there will always be some difference, just even if you give the, okay, let's think about it. If you give the treatment group the drug and the control group a placebo, right? And let's assume it didn't work at all, that there's no difference at all. Both of them were placebos, basically. All right? So, do you think, we were talking about the context of the SMART drug. So let's say the class was divided in half randomly, and half of you get the real deal, the drug, and half of you get the placebo. But assume it didn't work. Assume I just randomly divided you into 2 groups, just a random division. And at the end, I look at your scores, your overall scores. There's bound to be some difference because you're different people, just due to the randomization, right? There's bound to be some difference. The question is, how big a difference do you need before you can say, hey, the drug worked? Well, once we have, if we actually have a box model or an idea how we can, we translate something into a box model, we can calculate that. Think about it this way, okay? So the question is, how big a difference before you observe, before you can determine it's real, not just due to chance? All right, so the idea is, let's say there was only a difference of 1%. One group got an average of 99, the other group got an average not 99, that was so unrealistic. One group got an average of 80, the other 79 or something. And it went in the direction of the treatment group, the drug. Is that 1% big enough? Well, it would make a difference in your grades, you'd care about it. But could that happen by chance or not? So think about it this way. Let's say you just, there's two ways we can do this. One is experimentally, and we're going to come up with a sampling distribution of the mean. So what we do is we you just think about just make a random division, right? You just have everybody's scores and you randomly divide them into two groups, the scores, and then you compute the average of them. And you take the difference of that average, it's bound to be something, and you plot it on a histogram, right? And you do it over and over and over and over again. Well, the expected value is no difference, but it could go either way. It could go in favor of the treatment or in favor of the placebo, and you get some distribution of means, right? And you can do that. We will be doing that later in the course. We're going to look at these experimental histograms just by not using any of these idealized probability histograms, and we can just see it. But we know that that sampling distribution of the mean, or the difference of two means, is a normal distribution. We know that. We've seen that through, we've looked at the central limit theorem, that the sampling distribution of the mean with enough draws is normal. So we can use that. So all we have to do now is look at our observed difference and see where it is on that normal curve. And if it's extreme enough, we're going to say, wow, that's super unlikely, and we'll reject the null. So we'll say, it's probably not due to chance. It doesn't look like there's a random, I mean, think about it. What if there was a 20% difference? Like one group got 80%, the other group got 60% average. You really wouldn't need stats to tell you, but you'd have such a huge z-score, it'd be off the charts. It could still happen by chance, but the probability is tiny. So that's what we're going to be doing. All right, so let's walk through it. That's what motivates these. That's why these probability models have been so important. Because if we don't have a probability model, we can't calculate what the likelihood of seeing such a big difference is just by the luck of the draw. And that's known as the p-value. All right, so here we are. So basically what is this? It's a significance test is a statistical test to determine whether some difference we observe is real, meaning due to some particular cause, or just due to the luck of the draw. And what you do is you start off with assuming this null hypothesis, H naught. The null, it's the dull hypothesis, that it is just, you assume that it's just some chance, some probability model gave you this result. That how likely is it? And then we calculate how likely is it under the null. If we assume that it's just due to chance, how likely it is. All right? So this is basically, the null hypothesis is generally the hypothesis of no effect. Whatever we see in our sample is just due to chance variation. Okay? That's what it is. And so then we calculate what the probability is of seeing our test result. Is our test result likely to have come from a chance procedure or not? Okay, so that's all we're doing. And then we have this alternative hypothesis called H sub A, and that is that what we see in our, whatever effect we see in our sample, the difference between the treatment and control group results is too big to be reasonably due to chance. So then we reject that null and we say the treatment worked. Okay? Excuse me, why did I do that? It's here. I got these new glasses and I'm supposed to be able to see now. So I'm acting like I can't see still. Before I couldn't really see anything. All right, so now I can see. So Ellen, look here. So alternative hypothesis. All right, and you keep me to it. Make sure I'm writing in the right place because now I know I can see. I just have to remember I can. Okay, so the alternative hypothesis is that there's some other reason besides chance that explains the sample data, right? That our result would be very unlikely to be due to chance, that it's some other result. It's the hypothesis that the effect we see is real, okay? So we have these two competing hypotheses, and we assume the null. We assume the null to be true. That's the whole key. We assume it's just due to chance. That's really important. And we set up a box model based on the null, okay? And then from that box model, we get a sampling distribution, okay? We're going to get this sampling, we're going to pick a statistic so we can get this sampling distribution, and then get a p-value to see how likely it is. The p-value will show us where on that sampling, how far out it is. And if the p-value is very low, we reject the null hypothesis. All right, so that is the plan here that we're going to do. And why don't we go through? Well, here, let's just read this. So if this p-value is very low, like if you're way out on the tail, it's very unlikely to be due to chance, then we say we reject the null. But what's the cutoff? That's called the significance level alpha, is the cutoff. And we usually set it at around 5%. So if it's further, if the tail is smaller than 5%, if you're far out on that tail, we call the result statistically significant. Okay, so well, let's think about an example before we go on. All right, before we do any more abstract thinking about it. So now, let's say this is an example that came from my real life, back when I was teaching a large section years and years ago, large lecture of calculus, and it was divided into these sections, right? And I thought this early morning section, the people who signed up for 8 a.m. were probably going to do better on the exam. I thought they would. I also thought their TA, the TA who signed up, is probably a better TA. So I wanted to test this, and I thought, so that was my hypothesis. My null hypothesis was that, the null hypothesis is, of course, I always see differences between the sections, but, any random division into sections is going to result into, differences just due to the luck of the draw. I thought that this 1 8 a.m. section would have a bigger, larger average. So a large lecture had about 1,000 students. That's my whole population. And on the midterm exam, the class average, the whole population average, so that's mu, is 70. And this is sigma, and that's 12, all right? So that's what the whole class was. But I thought that the early morning section has more serious students and would therefore have higher scores. That section had only 36 students, so that's our n, and their average was higher, 75. So that's our x bar. So the question is whether this difference right here, this 5-point difference between what we observed in our sample, that's x bar, minus what we expected, the expected value of the average, what we expected x bar to be, the observed minus the expected, and that would be mu. I thought that difference, that 5 points, is that big enough to be due to chance or not? What do you think? How do you know? So you argue by contradiction. You assume that this 5-point difference right here is only due to chance, and you build a box model based on that. And the alternative is, that's too extreme a difference. That's so unlikely to be due to chance. So now you set up this box model, and the important thing is assuming the null to be true. You're not saying it's true. We know it actually wasn't true. I mean, they weren't randomly assigned, but we're going to model it that way. So we assume to be true. We assume the null. We assume what? That we imagine putting all these 1,000 scores, one for each student, and on each is going to be written in an exam score, what they got on the exam. And we're wondering, there's going to be chance variation just due to the luck of the draw. So we know in this case that the 1,000 students had an average of 70, and that sigma was 12. And now we're wondering, if we drew, let's just assume this is true to see what our typical chance variation would be. All right, so we draw out of here, we're going to draw what? Our sample size, which is 36 students, the section size. N equals 36 of these tickets, and obviously without replacement, they're separate students. And then we observe our observed x bar, our observed sample average what we got with the 36 students was 75, when we expected what? We expected a sample average coming from here of 70. What else would you expect, right? So the question is now, all right, so now we know this difference. And what we're trying to figure out before we even do this, well, we know that the sampling distribution of the mean follows the normal curve, right? We know sigma. Maybe I should write this down on a big piece of paper, because I want you to get a feel for what we're doing here. So let's just take a sheet of paper here. Let's see. Let me see. All right. So what do we know? We're not going to use a t distribution. Why? We know sigma. So t is out, right? Now, why do I think I'm going to use a normal distribution? I'm looking at the sampling distribution of the mean. Of the average of x bar, okay? Now, remember, because of the central limit theorem, we said if n is large enough, and n is 36, that's pretty big. If it was a really, really skewed distribution, we do have a skew. Okay, so our distribution, I want to get real about this because this is important. Our distribution for the exam averages are like this usually. So it's not usually normal, okay? But you can still do this because it's bounded between 0 and 100. So there's not these really, really, really extreme values out there, okay? So if you're really going to think about it, they'd say, oh, all right, if you did this, you'd see that rather than just having the rule n is greater than 25, in cases like this, it certainly works. If it could go out forever in either end, then, and we thought there was really extreme values, then we'd have to go larger than 36. All right, so n is equal to 36, so central limit theorem kicks in. The reason I'm really want you to understand this is because you're going to see the p-values over and over and over and over again. So I'm acting as if you're really researchers right now because it's so important. And not just for this exam or some course. Since we don't have real extreme values, that looks pretty close enough to normal, 36 is good. It's not just because it's over 25, like the rule for an exam or something. This would be good. All right, so now the sampling distribution, okay, so that means we can use the normal curve. All right, so we can use z. So let's think about it. So we have this z. So we know that this is the sampling distribution of x bar, right? And as a z-score, we know right in the middle is 0, right? As an exam average, what do we expect? As x bar, which is an exam average, what do we expect? Well, we expect since the box was 70, that's what we'd expect. That's our expected. And now the question is, this 5-point difference of 75, how rare is it? Once I change it to a z-score, where's it going to land on here? That's what we're going to do. We're going to change it to a z-score. And so where's it going to land on here? So I just want you to think about it and mark somewhere in your mind just what your intuition would tell you. So where do you think it's going to be on this curve? 7, do you think it's just a tiny little difference that could easily happen by chance? Do you think it's sort of like here, 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 is here? Where? So you have in your mind an intuitive picture. Okay? Do y'all have that? Because think about it, where you think, what your intuition is, without even thinking about the calculation. So now, all right. Now, let's see where it is. So how are we going to do this? How do we translate our 75 into a z-score? Well, now we can, right here, we can think, okay, we can just do it here and then fill it in. All right, so we're going to change it to a z-score. So what do? We take our value, which is our observed value here, minus our expected, observed minus expected, right? Our expected value, over some standard error, right? And we're talking about averages, so they're all going to be averages. So our observed x bar, that's what we're going to do right here. Our observed x bar, we can do it right here. Z equals, our observed x bar is 75. minus 70. So there, right there is the 5-point difference. We know it's 5 points. We just don't know what it is in terms of standard errors. Remember, these standard errors are going to be like 1, 2 is like, that's only 5%, and then 3 is way out here. All right, so where is it on here? -1, we know it's not that direction. -2, -3. Sorry, I'm making it so messy. All right, so where is that 5-point difference? Is it just right here, here, here? So now we say, okay, we know it's 75 minus 70, which is 5. And we just have to figure out what one standard error translates into. So that standard error is what? Can you remember? SD over the square root of n. And we know, or sigma. It should really be sigma over the square root of n. We know sigma in this case. And what is it? 12. And what's n? 36. So we have 2. So that's where 72 would be. That's where 74 would be. And 75 is going to be way the heck over here. Really, really far. That's our 5-point difference. It's enormous. And I bet you didn't think that. Very few people would have. We don't have good intuition about that. It's 2. So when we put a 2 in here, 2 here, we get 2.5. You know, that takes you to 72, that 2. 74 and halfway to, so that is what we're doing. Just when I get enthusiastic, I like to write big. So now I'm going to make it pretty in your notebook, okay? So we'll make it pretty in the notebook here, and we'll just do the same thing. So here, we're going to put in the standard error of the average. And that standard error of the average, if you haven't written it down yet, that's just sigma over root n, which is equal to 12. In this case, we know it, over the square root of 36. So that is 2. That's what we put here, and that's 2.5. All right, so now, when we draw the normal curve, right? So we'll draw the normal curve here. And we have 0, and that's right here. That's our expected value, which is 7. And we want to know where to place 75, and we found out now it's 2.5. So we're going to look up 2.5 in the back of the book. It's going to be a huge, it's going to be a tiny, tiny p-value. So we look up 2.5, and it's 98.76 in the middle. All right, so now we have 98.76 in the middle. What does that leave in the two tails? That's really going to leave less than 1%. 1.24, so that's 0.62 in each tail. So it's a tiny, tiny. That's where 2.5 is. Between 2.5 and negative 2.5, this little piece right here, the probability that we would have gotten a 75, this 5-point difference, translates into a probability, this, of what did I say, 100 minus 98.76 divided by 2. So that's 1.24 divided by 2. So that's 0.62%, less than 1%. That's tiny. That's a little dot. And I don't think, you know, when I was looking at it, when I just, even after doing statistics for so long, I looked at it and I thought, it's not as big, such a big difference. And then I just did the calculation and I said, oh my goodness. So this is what I'm saying is, this is the beauty of statistics. It keeps us, it gives us these tools that are so far from what we're hardwired to have. And so it makes us extraordinarily smart about numbers and about uncertainty. It's amazingly, that's what I want you to understand, is how useful it is. And not just because you're going to pass tests, but because I want you to think about making decisions in the real world this way, because we really need it. Okay? So Now we get this p-value. That's what's called the p-value right here. And what is this p-value? Okay, this is the sampling distribution of x bar. That's what this is, and maybe we should write this down. And so this is the sampling, and I should write this in the next notebook. This is a fairly new notebook, and I'm realizing as I'm teaching things I have to put in. So this is the sampling distribution of x bar. That's what this is. And we can do it. It's not t because sigma, I'm just going to put, it's normal, not t here. We're not going to use a t distribution because this right here, sigma is known. So we'll never use a t when sigma is known. The whole point is that it follows a different distribution when you have to estimate. But it follows the normal as long as the central limit theorem kicks in, and it does here. All right, so that's that. Now, this p-value, what is it? What is it? It's the probability we'd get if the null was true. That's what this is. P is the probability we'd get of what? We'd get of the probability we'd get of to see. With probability we'd get, that's a bad way of wording it. It's the probability, I guess we'd see, it's the same thing, and a sample average in x bar greater than or equal to 75 if the null was true. It's the same thing as get or see, sorry. It's just a probability when we did this randomly that we'd get a 5-point difference in this direction or more. That's why it's extending out. We're saying the probability we get this big a difference or more, that our x bar would be that if the null was true, if it was just random. So if you get a really small value of p, that's strong evidence against the null. It indicates that maybe something besides chance was going on. So what we do is we reject the null when p is small. And here's something, how small does p have to be to reject the null? Well, people like a cutoff, right? So where's the cutoff to reject the null? If p is less than 5%, this is an arbitrary cutoff because people like cutoffs to make decisions. We're going to make a decision here. You know, if it was a treatment, we'll say the treatment worked. And here at this point, we'll say we want to make a decision. So it's like, you know, it's an arbitrary cutoff that we use 90% for A, and then lower than 90% is B. Right? But why are we doing that? It's just because people like to make decisions, right? It's way more informative to give your actual score. To say you got a 90.1 and an 89.9, they're almost the same score, yet on your transcript it looks very different. So people get bent all out of shape because we have to make some decision. I'd much rather just give the score. Same here, I'd much rather give the p-value. And if you're, this is a very small p-value. And to say just, the usual thing is that people use 5% as the cutoff. Well, what would that give us in the tail? That would give us 5% in the tail, which would be a z-score of 1.65. I mean, it would be way over here. This is much smaller than that. And this is arbitrary, okay? So, but there's no justification, but it's a convention. And you'll see this all the time. So when people see less than 5%, we call it the statistically significant, and we say that's so small, and we reject the null. And if it's 1%, it's highly significant, and we strongly reject the null. I don't know, you know, it's like more evidence. So then you'd like strongly reject the null. All right, you know, reject, even have more evidence to reject the null. Reject the null big time, I don't know, with exclamation points. These, I don't like these very much. I think it's much more important to report the p-value. But how are we going to phrase this? We'd say, okay, if we really got this result, we'd say, and you were writing a paper, you would say, okay, it's highly significant. Our p is less, our p is less than 1%. It's 0.62. So result is highly significant. Of course, we're going to reject the null. But what would be our conclusion? Now, we haven't really proved the alternative. We don't even have a specific alternative. We just know that we think that there's some particular cause. We don't know if it's because the students were better, the TA was better, or it was just a tiny chance and it really was random. We don't know yet, but it's very strong evidence. So we'd say it's extremely, and we'd probably do more tests, very strong evidence. That's a very tiny p-value. That something besides chance is going on. We don't really know what. We certainly haven't proved that the students are better. We're not sure. That's a very good guess. Very strong evidence that it could be the TA's better. It could be some other thing. So very strong evidence that something besides chance is going on, that there is a particular reason. Now, why don't we just accept the null? Why don't we just accept the null? If it was, let's do an example where we're going to accept the null, and you'll see why we don't just accept the null. I mean, if we had a huge p-value. Let's move on. Okay, so now example 2. This is a very typical example right here. This one, much more typical than the previous one. All right, suppose a large university claims that their average ACT score of their incoming freshman class is 30. So this is our mu right here, but this is a claim. But we think that the university might be inflating their average. The universities sometimes do this to get US, so their ratings get higher. So we're doubtful about this. So we decide to test the university's claim and take a simple random sample of n right here equals 50 students. That's our n. And then we find that their average, x bar, is less than that. Like we expected, it's 29.1. With a standard deviation, this isn't sigma, it's the sample standard deviation. So this is the sample ST of 4.5. All right, so now let's formulate the null and alternative hypothesis in terms of a box model, okay? Well, the null hypothesis is that what? That this claim is about the population. The null is always a claim about the population. In this case, it's a claim about the parameter, the average of the population. And he's saying, the professor is saying, that the population parameter is 30. All right, and that this difference we see between the sample and is small and just due to chance. And we're doing that versus the alternative, and that's the more interesting, that he's inflating it, and really that mu is less than 30. That's what we believe. And that's why we're testing that claim, okay? So we have this box. We assume this is true. You always assume H naught is true, so we're going to do that. So we got this box here. This represents all freshmen. So it's going to have, this is the population. So it's going to be all freshmen, all thousands of freshmen. On each is written what? Each ticket is written an ACT score. And he's claiming that mu is equal to 30. So we're assuming that's true. We're saying if that was true, how likely would we be to get such big difference? All right? Just by the luck of the draw. All right. So, and then sigma we don't know. All right, so now we're going to compute So what are we doing from here? We draw from here. N is equal to 50, and it's always without replacement, right? And what do we observe? And we get an observed X bar of 29.1, and we have an expected X bar of 30. So we have that difference there. All right? Now, so we're going to do this test statistic, and what should our test statistic be? We don't know sigma, so should we use T or Z? What should our test statistic be? Our test stat, should it be Z or T? It's an unknown sigma, so we really could use T. There'd be nothing wrong with using T. We could use T, and probably software would, but I know the sampling distribution is going to be so close, but since N is equal to 50, Z will be a very good approximation. So let's just go ahead and use Z. Z will be a very good approximation. What I want to stress is that it's possible, whenever you don't know sigma and you have basically a normal population here, you should use the sampling distribution will be T if you have a normal distribution. And ACTs are pretty normal, even within a restricted range like this. They're probably, no, not real normal, but it's not far from normal. I'll say because of central limit theorem. So that's the reasoning. You won't be wrong if you use T. But Z is so easy to do in our heads, and let's just use it. All right, and you're going to get a very similar answer. So Z is going to be our observed minus the expected over some standard error, right? So in this case, what do we observe? This average of 29.1 minus our expected of 30 over some standard error. And this is the standard error for the average. So what are we going to do here? So that's sigma over root n. Now, you could, if this 4.5 wasn't SD plus, you could adjust it there if you want. But in this case, n is big enough, we're just going to leave this as 4.5. We're going to estimate it with this. So we're going to estimate, we're going to take this 4.5, and we're going to use that to estimate without even changing it. Okay? And it might have already been changed. We haven't even been told. It might have already been SD plus, but if it wasn't, it's fine. It's big enough. So just for the purposes of we're just going to use that. Okay? But by the way, it's fine to make this adjustment and still use Z. It's fine to make SD plus and still use Z. People just don't generally do it. They don't bother. Okay? So sigma over n, so we're going to do the estimate, so that's 4.5 over the square root of 50, and we get 0.636. That's what we put in here, 0.636. And then we get negative 1.4, and that is our z-score. All right? So now, we're going to draw a z-curve, because there's just one z-curve. It's so nice. That's what the huge advantage is, and we know basically what it looks like. Okay, so in the middle is 0. As x bar, which is what ACT averages, ACT average, what would we expect? 30. We got a 0.9 difference. Turns out the standard error is 0.6, so it's just like 1 and 1. Okay, so it's going to be right here is where 29.1 is. That's our observed, that's our expected. That difference of 0.9, negative 0.9, works out to about 1.5, 1.4 standard deviations. Because 1.4 would take you down 0.6, and then we went down. Okay? So we look that up, and it's about 84% approximately. And so now, what is that? So 16 and either tail together. So this right here is 8% of the whole. So P is equal to 8%. So now you'd think, okay, we can't reject the null. P isn't less than our standard cutoff of 5%. P is not less than 5%, because it's 8%. All right, so that means what? Should we accept the null? We can't reject it. There's not enough evidence to reject the null. So there's not enough evidence to reject the null. Basically, P is not small enough to reject the null if we set the significance level at alpha equals 5%. That's the typical one. We don't have a small enough P. So what are we thinking here? Why don't we just say accept the null? You know what? I think the best analogy that I can give you is our justice system. Okay, so let's just, our justice system, just for these p-values. So the analogy would be, have you ever heard the phrase, well, first of all, in American justice systems, we assume innocence. Innocence is the null. So you assume the null dull thing, that the person is just an ordinary citizen, the defendant is innocent. Innocent. Most, you see. There's no reason to think he's a murderer or whatever, he's innocent. So you assume the null. And then you have evidence against the null. So you assume, all right, so you could have evidence against. So you assume that nothing's going on here. And for most people, we're not going to have airtight alibis. So we're going to have like some evidence against us. Maybe we knew. So we accumulate evidence like, maybe the defendant in a murder trial, maybe the defendant had a motive. There was a fight going on. He was seen at the crime. There were eyewitnesses, blah, blah, blah. If there's DNA evidence, it goes way, way, way out here. If there's an eyewitness and so forth, at some point, you have to make a decision. And this, like here, this was what people call beyond a reasonable doubt. You've probably heard that expression. So you have to decide that the person is, you convict because beyond a reasonable doubt. And this little bit of doubt, the doubt gets so small, the little doubt that we still have, that little is equal to our p-value. With DNA, I'm going to zoom out a little bit. So this is like this is our justice system. You assume, it's an argument by contradiction. You assume the defendant is innocent, right? That he's innocent. And then you accumulate more and more and more evidence. And at some point, you have to make a decision. Or, we just have to. Now, we can't quantify it, but we just say, and at some point, and this right here, this little bit of lingering doubt, because nobody knows for sure, except the defendant himself, and sometimes they even get confused, or God, or who, if you believe in God, that's the only one who knows the truth. You don't. But you make a decision under uncertainty, and that's what you do. And you say, okay, beyond a reasonable doubt, and that little bit of doubt is your p-value, okay? That's the idea. But then, let's say it's right here. It's not quite. You have too much doubt. Too much doubt. You don't say he's innocent. You don't think, oh, that defendant is innocent. We haven't proved he's innocent. We assumed he's innocent. We just say we don't have enough evidence to convict. So we don't accept the null because we assume it to begin with. You never say, okay, he's innocent. We just say he's not guilty. We don't have enough to convict. It's the same thing. So, all right, so that's where the double, people think it's a double negative or whatever. It's just that we don't have strong enough evidence. We've assumed innocence. We have a lot of evidence maybe, but just not enough. If more evidence came in, maybe we'd make a different decision. That's how you should be thinking about it. So I don't want you to say, okay, we accept the null. No, we just don't have enough evidence to convict, to say there's something else going on. Does that make sense to people? All right. So let's move on. Now, let's see. So we're going to do this one fairly quickly. So Z can also be used for sums and percents. And so this one is, sums and percents are really similar. I want for 0, 1 boxes is what I want to show you. So this is a Z can be used for a 0, 1 box. That's what we're going to do here. All right. So these experiments on ESP are done all the time. This is a real experiment because people are always trying to prove that there's ESP. Okay. So this one is, these people claim to be clairvoyants. They had a machine where they used a random number generator to pick one of 4 targets. Okay. So you have this, think of it as, you have one of 4 targets. 1, 2, 3, 4. And the people claimed, okay, the subjects try to guess which target the machine had chosen. The machine was in a different room, right? So there were 15 clairvoyants, each one of whom made 500 guesses, right? So that here is our N. So we had 7,500 guesses made. That's our N. Now, each one of them, it's like a gambling game. So you make the box for a single play. We're assuming the null is they're just guessing. So it's just like they're guessing from a box that has 1, 1, and the rest are 0. That's the null. So, but they say they can do better than chance. Of these, they got 2,006 right. Well, how many would you expect to get right? You'd expect 1/4 n times the average of the box. The expected value for the sum would be 1/4. That's 1/4 of the draws. Yeah, that's n. 1/4 is the average of the box. All right. So they had 131 extra correct. Can that be explained by chance variation? So what are we doing from here? We're taking n is equal to the 7,500. It's like a gambling game without replacement, right? Because there's only 4 in here. We want to keep the odds the same, right? And the null is, they're just guessing. And this 131 correct is just due to the luck of the draw. So they're just guessing. And the alternative is no, they're not guessing. Something else is going on. Not necessarily that they have ESP, but the chance that it's too big to be due to chance. All right, so now our observed sum is given to us right here, 2,006. And our expected sum, that's the expected value, would be equal to n times the average. The average here is 1/4, n times the average of the box, because it's for, the sums. So we have 1/4, we did it right here, times 7,500, and that's how we got this 1875. All right, so this difference here between them is what we want to say, is it big or small? So we're going to do a Z because we know that we don't have to, no possibility of doing a T because this box isn't normal. The standard deviation we can figure out directly from this average, right? So there's no possibility of doing, it's a 0, 1 box. You never use a T for 0, 1 boxes, never. So we're going to be doing a Z here. We know the sampling distribution of the percent is normal with enough draws, and this is certainly enough draws, is really going to be a great approximation. So we're going to do observed minus expected over our standard error, and that's where we get this difference here. We observe more than we expect. That is our 131. The question is, just even before we figure that standard error out, is this. We know it looks like normal. We know in terms of a Z-score, we're going to have a 0 in the middle. But now, in terms of the sum, our sample sums, these are our sample sums, we'd expect right in the middle to have 1875. And where do we put these 131 extra? Is it really crazy or is it right? It's just only 131 out of 1875. Where do you think it's going to be? Well, we don't know till these are sums, so we're just going to compute that. Remember what that is. This is the only time, so SE sum, let's write it down. So SE sum, SE is an SD, right? So just put that down right away. Now, sum, we have that square root of n. Are we going to multiply or divide? This is the only time you multiply, all right? So we're multiplying the SD by the square root of n. So the SD, you know the SD of this box. It's like 1 minus 0 times the fraction that had 1/4 times 3/4, 0.25 times 0.75. That's the SD. And then n is 7,500. So we do that, and if we do that, we get 3 point. This is about, what do we get? This times this, I got 37.5. That's what I got. So that's what we put in here, 37.5. And now you see this astronomical z-score. Astronomical. You know it's going to be way, 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 way out there. Okay? That's a huge z-score. 99.95% is within this right here is 3.5 and negative 3.5. And that's where the 2006 or the 131 extra guesses winds up. So we have a spec here. And what is P? So P is going to be 0.05 divided by 2. So it's going to be 0.025%. 100 minus that divided by 2. So what do we conclude? Oh, P is so less than 1%. So we're just going to reject the null hugely. With exclamation points. I mean, but does that mean there's ESP? No. What does it mean? They never were able to repeat this. So there's a lot of reasons they thought they were cheating. But we can't conclude, but cannot conclude ESP. This is a true experiment and they couldn't repeat it. And there were a lot of different things that might have been going on we'll talk about them later. I mean, it was one result. They've done this thousands and thousands of times and they haven't been able to do this. So once in a blue moon, you will get a result like this. So it could have been honest, but it could have been faking it too. Okay, we reject the null here, but we repeated it and it was never able to be repeated. All right, now I want to talk about the t distribution, all right? Because we're going to do an example now on chapter 13 in the last few minutes using the t. So recall when we use this t, when you have this small, basically the most important one is this. You have an unknown standard deviation. Okay? Now, if you have an unknown and you have an approximately normal distribution, like percent, they're not normal, they're 0 and 1s, that's not normal at all. If you have an unknown and an approximately normal distribution, close to normal, you're going to have a t distribution. That's a t. That's your sample mean is going to follow a t distribution. So you can always use it in those cases. But you don't really have to. So we're only saying, because it's such a hassle to use it, under these conditions, after about 25, samples out of 25, for our purposes, you're going to get the same, pretty much the same result. So we're only going to be using it for the small. But software, once these two conditions are held, software is going to use it. All right, and what's the difference? The difference is you do make two adjustments. One, you're going to divide through, basically, when you're computing a standard deviation, instead of dividing through by n, you divide through by n minus 1. And you get this SD that's always bigger than because we're dividing through by, it has more, your uncertainty is bigger because you're estimating the SD. So your estimate of the SD is a little bit an underestimate. Think about it. What if you only have a sample of 2? Okay? You only have a sample of 2. How do you compute your SD from that? You'd look at, if you just have a sample of 2, you'd look at how far they are from their average of the 2, from the average of the 2, right? Well, aren't they going to be closer to the average, to their own average of those? You get a sample of, let's say you get, I don't know, 4 and 5. So your SD is just going to be 0.5 because you're halfway between, right? The average is 5 and one's 0.5 above and the other's 0.5 below. So your SD is likely to be closer to your sample average than to the average of the box, right? It's going to follow, so it's going to be it's likely to be too small. And the bigger, so it's going to be an underestimate. And if you, we can go through this longer, but first I want to go through the logistics of, so we'll talk about this over and over and over again. What the degrees of freedom mean, why we're dividing through by n-1, but it's a long discussion that's going to be recurring, so I just want to give you the logistics of how it's going to change, all right? And then we'll do it we'll go into the theory behind it another time. All right, so let's just look at the same example that we did before in example 1 with the difference between 75. We had this difference, okay, between 70 and 75. It's the same thing, but what's different here? The standard deviation is now unknown, and we are approximating it from our sample. And we also have a small, and we're also assuming that it's normal. So in this case, we for sure are going to use the t. All right, so we have this box. It's the same thing. We have all 1,000 students in here, 1,000 tickets. We still know mu is 70, but we don't know what sigma is. That's unknown. So what's going to change is we are going to, now we have the sample of 16, and we observe an x bar equal to 75. This is all the same. We expect our x bar to be 70. And now we have this sample SD. This is our sample SD equal to 12. And we're not going to just use that 12 to estimate it because our sample size is so small, we are going to adjust it. So we're going to adjust it by n over n-1. 16 divided by 15 times 12. And that makes it a little bit bigger. So now we use this, SD plus is a little bit bigger, and that's what we're going to use to estimate. So now when we get back down here, what are we going to do? We're going to take that difference between, it's the same exact thing, 75 minus 70, that's our 5-point difference. But now, instead of using, we're going to say our standard error, we'll call it plus for the average, is going to be SE plus over square root of n. So we're just going to say 12.39 over the square root of 16. So that makes it a little bit bigger than what we had before. So we'll do, oh, excuse me, that's 3.1. I'm jumping the gun here. That's 3.1. Before we had 12 over 4, 3. So that made it 3.1. Before, remember our before our SE average was equal to 3. Now we have S plus average, 3.1. So this is going to be 1.61. Our T statistic is 1.61, whereas our Z was what? Our Z was bigger. Where is it? Oh, our Z was bigger. Why? We had a huge sample size here. That wasn't the big difference. Here we have a sample size of 36. That's why we, okay? So I'm sorry, I was sorry about that. It wasn't before. I'm just saying if we didn't, what am I talking about? I'm just saying if we didn't make the adjustment, that's all. Before we had this, we didn't have 16 down here. We had 36, and that's what made it different. But if we didn't use it, what would be the difference? Instead of 3.1 down here, we'd have a 3. So that doesn't change things that much. But now we have to look on the t-curve instead of the normal. All right? Did I confuse anybody? Is everybody with me? Nod if you're with me. Okay, thanks. All right, so we've got this t. And all I wanted to point out that t would be smaller than the equivalent z. But all right, but this is the big difference. We can't use our normal curve. So now there's like all these different t-curves we can use. Which one do we use? They get closer and closer to the normal, but that depends on our degrees of freedom. And basically, it's n minus 1 because we had one parameter that we used on the way to getting our SD. We had to use the mean. All right, so it's n minus 1. We'll talk about that more, but that means it's 16. How many degrees of freedom? N minus 1. So that's 16 minus 1, which is 15 degrees of freedom. So we have to use this t-table. It's going to look like the normal curve, right? But it's going to be fatter in the tails, and it's a different one for each degree of freedom, so we don't know which one to draw, so we have to go to the table. So we go to the table, and now, degrees of freedom. All right, so only focus on the one for 15 right there. All right, now, how are we going to read this? Well, ours was 1.61. So you see, these are the t statistics. So ours was 1.61. It's between 1.34 and 1.75. So that means that this tail, the one tail, is between 5 and 10%. These were the confidence intervals. This gives us the area in the tail, and it's symmetrical, so it's for one-sided. So all we can say is P is using that table. So all we can say, we can't even draw it here. Using table, we can conclude what? That P is between 5% and 10%. Why don't we get a better P? Why don't we get a better value for that? So we can see. So you could just go here, and you would look here, and we do our p-value. And we go to our t. And the degrees of freedom are what? 15. And we have a p-value of 1 point. It's negative, right? No, it's positive. 1.61. 1.61. And we get 6 point, so that's what it looks like. 6.4%. All right. So we can draw it on here. And we'll go back to the document camera, and we'll draw it. So, 0. We get this is between 1.61 and negative 1.61. We got this was 6.4%. So, you know, it's getting close to the 5% mark. Should we reject the null? Can we reject it? No. Not enough evidence. No. We can't reject the null. We're not far enough out. We almost are. Not enough evidence if we're using at the significance level that's demanded for most things, alpha equals 0.05 or 5% is how they say it. Okay? So, no, not enough evidence, but it's close. You know, maybe if we got a little more evidence, we would be able to reject it, a bigger sample. So that's the idea. And I think it's really, I'm trying to stress how to think about this, and so it's intuitive to you because it comes up all the time. Any journal article that you read is going to give you a p-value. So I want you to understand what they mean. All right? And we're going to continue with this next time.